All right, today we're going to talk about microbiology. But listen, this isn't your boring high school science class. Forget just germs and lab coats. This is a story, an epic one, really. It's about creation, incredible discoveries, and a hidden empire that literally built our world before we ever showed up. So let's dive in. You might think a story about microbes starts on Earth, right? Nope. Our story actually starts out there, in the heart of a dying star. We're talking billions of years ago. These massive explosions, supernovas, were cosmic forges. They created all the essential stuff, carbon, nitrogen, oxygen, the very building blocks that would eventually make up every single living thing, right down to the very first microbes. And that right there, that's the key thing to remember. For billions of years, microbes had this planet all to themselves. They were the only game in town. And in that time, they literally terraformed Earth. They took a nasty, volcanic rock and turned it into a living, breathing world. I mean, they created our atmosphere, the soil, everything that we and all other big life forms depend on. They're the true architects here.
So, that begs the question, right? How did it all even start? How does life just spark into existence on this hot, hostile, volcanic planet? Well, that's what we're tackling first. Let's look at the primordial blueprint for life itself. The amount of time we're talking about here it's just mind-boggling. Think about it. For more than 500 million years, Earth was just this searing, molten ball of rock, totally inhospitable. But eventually, it started to cool down. And as it cooled, water vapor turned into vast oceans. And deep down in those oceans, in the crushing darkness around these hydrothermal vents, something amazing started to stir.
Okay, so here's where it gets really cool. There's this idea called the RNA world hypothesis. We all know about DNA, right? The famous double helix. Well, the thinking is, before DNA, life probably got its start with RNA, its simpler cousin. And why RNA? Well, it's a bit of a multitasker. It could do two jobs at once. It could hold the genetic blueprints, and it could act like a little machine to copy itself. It was basically the perfect all-in-one starter kit for life to get going. So from these first little self-copying molecules, life starts to branch out, to diversify. But what's truly incredible is that the genetic evidence points to one thing. Every single living thing on this planet today, I'm talking from a tiny bacterium all the way up to a blue whale, can trace its family tree back to one single source, a population of cells we call LUCA, the last universal common ancestor. In a very real sense, we're all family.
Okay, so for billions of years, this whole microbial world is just doing its thing, completely invisible to us. So how did we finally discover it? How did we pull back the curtain on this hidden reality? Well, it took a game-changing invention.
Believe it or not, it all starts with some eyeglass makers back in the 1590s. They were just messing around with lenses and voila, they invent the first microscope. Fast forward a bit to 1665, and a guy named Robert Hooke looks at cork and sees these tiny little boxes he calls cells. But the person who really blew the doors open, that was Antony van Leeuwenhoek.
So get this. In 1676, Leeuwenhoek, who wasn't even a formally trained scientist, he was a merchant. He takes a drop of water and looks at it through his homemade microscope. And what he saw absolutely blew his mind. A whole world teeming with what he called little animals. Tiny creatures just swimming and zipping around. It's an incredible moment. It was the first time any human had ever seen living bacteria. And you can imagine, this discovery just unleashes this massive question. A question that scientists would argue about for the next 2 centuries. If these little animals are everywhere, in the water, in the dirt, even in the air, where on Earth do they come from? Do they just poof appear out of thin air?
And that set the stage for the great debate. You had 2 camps. In one corner, you have the idea of spontaneous generation. This ancient belief that life can just spring from non-living stuff, like maggots just appearing on old meat. And in the other corner, you have this new idea, biogenesis, which says, nope, life only comes from other life.
One of the first big hits against spontaneous generation came from a guy named Francesco Redi. His experiment was so simple it was brilliant. He took 2 jars with meat. One was open, the other was covered with gauze. And guess what? The open jar got maggots, because flies could land on it. The covered one? Totally clean. The takeaway was crystal clear. No flies, no maggots. Life wasn't just appearing.
But that was for maggots. For microbes, the debate kept going until Louis Pasteur finally settled it once and for all. His setup was genius. He used these special swan neck flasks. He'd boil broth in them to sterilize it, right? But the cool part is the S-shaped neck still let air in, so nobody could say he was blocking some vital force. But what it did block was dust and microbes from the air. They got trapped in the bend, and the broth, it stayed perfectly clear for ages. But the moment he tipped the flask, just enough for the broth to touch that trapped dust, bam! It got cloudy with microbial growth.
And just like that, with one incredibly elegant experiment, a theory that had been around for 2,000 years was completely shattered. Pasteur proved it. Life only comes from life. Case closed.
Okay, so if life only comes from other life, and we now know these microbes are everywhere, that leads to the next logical and maybe even more important question. Could these tiny little things be the reason we get sick? This is where the germ theory of disease comes into play.
Proving it was the trick, and a German doctor named Robert Koch came up with a system, a set of rules that are basically a detective's handbook for finding a microbial culprit. Rule 1. The microscopic suspect has to be at the scene of every crime, in every sick patient. Rule 2. You have to catch the suspect, isolate it from everyone else, and grow it in a lab. Rule 3. You have to prove it's the real killer, by showing that it causes the same disease in a healthy host. And finally, Rule 4, you have to recapture the exact same suspect from that new victim to be sure.
And this is exactly what that process looks like. You go from the sick animal, to isolating the bad guy in a lab dish, to proving it causes the sickness in a healthy animal, and then finding it again. It's a complete loop. For the very first time, science had this rock-solid, step-by-step method to pin a specific disease on a specific microbe. It totally revolutionized medicine.
All right, I know what you might be thinking. This is all really interesting history, but why does a set of rules from over 150 years ago still matter? Well, the truth is, these core ideas are being used every single day, and often in places you would never, ever expect.
Let's take a real-world example. Imagine a brewery. We'll call them Brewtech. They've got a huge problem. Their beer quality is all over the place. One batch is fantastic, the next one, not so much. And for a brewery, that inconsistency is a business killer.
So how did they fix it? They actually turned to history. They started using microscopes to look at their yeast, just like Leeuwenhoek did with his little animals. Then they basically used Koch's rules to isolate different yeast strains and figure out which one made the best beer, every time. And of course, they used Pasteur's ideas about sterilization to make sure no unwanted microbes were crashing the party. It all connects.
And that's the big takeaway here. Whether we're talking about controlling diseases in a hospital or just making sure the beer you drink tastes good, the work of these pioneers isn't just stuff you read about in a history book. They are the fundamental tools we are still using right now, every single day.
You know, Louis Pasteur really nailed it when he said, "The role of the infinitely small in nature is infinitely great." And it's so true. From the stardust that built our world to the tiny yeast that makes our food and drink, the story of the small is, without a doubt, the biggest story there is.
It's amazing how far we've come, isn't it? From squinting at blurry little animals in a drop of water to engineering microbes to create life-saving drugs. The whole journey has taken us from stardust to sterilization. And it leaves you wondering, with this vast, invisible empire all around us, what is it going to teach us next?